Hello, my name is Radek. I have pleasure to be chairman of our afternoon session, and pleasure to welcome Patrick. Patrick is going to talk about extremely interesting issue about adaptive machine learning models. Patrick, floor is yours.
Thank you. It's a pleasure to be here. So my name is Patrick Deziel. I'm a machine learning engineer and AI specialist at Rotational Labs. So Rotational Labs is a startup where I build custom AI ML solutions for our clients. I'm primarily a Python and Go programmer. Most of the code in this presentation is going to be Python. So just like a little bit of background, I'm from Minnesota in the States, and I like to do some rock climbing in my free time. So today's talk is going to be about real-time machine learning. So we're going to start by explaining what real-time machine learning is, and we'll look at a few examples of real-time machine learning in action, and then we'll go and talk about what real-time machine learning has to do with LLMs. So the basis, real-time models utilize real-time data to adapt to changes in an environment. So some examples of real-time data that you might interact in the real world are real-time APIs. So there are a few real-time APIs I've used in the past. There's finhub.io, which you can get live financial data about markets and stocks and stuff like that. Another interesting one is the OpenSky network, which exposes a lot of publicly available air traffic, which you can use for some interesting use cases. But we should also not discount other types of feedback. So there is user feedback, which if you're using an app like Netflix or in the past Pandora, those are examples of recommendation systems which are constantly ingesting feedback from users in order to present them with recommendations. So that is also an example of real-time data. When we talk about offline learning versus online learning, so real-time learning is also sometimes called online learning because the learning happens in an online fashion. The difference between these two approaches is that in offline learning, the learning happens in development. In online learning, the learning actually happens in production, which is a bit trickier. So basically in online learning, rather than training on a large data set, you deploy a model into production, which learns from its environment and hopefully converges to a model which is usable and can adapt to changes in the environment. So when do you use online learning? Mostly it's used to compensate for the idea that your models will become less useful over time as the nature of the data that you're training on changes. So basically, there are two ways this can happen. One is feature drift, where your input features change. So, for example, if you train a spam classification model on shorter emails, but in production you actually observe a lot longer emails, that could adversely affect your model. And the other thing is concept drift, which happens when the relationship between your predictive features and your labels changes over time. So mostly this is due to external factors that you didn't really account for when you were training, such as like a disease outbreak or some economic situation happening, which is they may be transient things that traditional machine learning models may not be able to handle. And also, if your recent data is more important than historical data, online models usually trend towards biasing recent data more than historical data. So if you have a forecasting use cases, or you want your model to be weighted towards user preferences, those are kind of two use cases where this comes into play. So there are some risks to real-time machine learning that you should be aware of. One is catastrophic forgetting. So this is the idea that if you train an online model with new knowledge, it could potentially forget older knowledge. And in batch learning, you would usually realize this because you're constantly validating your models when you train them, right? But in online learning, you have to be more careful about the models that you're training because they might start to diverge from the original use case. So we have to be careful and include guardrails and mitigation strategies to ensure that the model remains accurate and is still producing safe outputs for production use. And then lastly, event-driven workflows are just really hard to implement because they require a lot of specialized expertise in dealing with stream-oriented architectures, which is different from maybe some like synchronous architectures that you're familiar with. So you have to end up using like event-driven data streams and those type of architectures. Okay. So now we're going to get into some examples and see how real-time machine learning works in practice. So this is an example of online regression. So in offline regression, let's say linear regression, what you're doing is you're trying to train on a data set to learn model parameters to predict some value, like maybe you want to predict the value of a stock price for the future. So you use a bunch of historical data to do that. In online regression, it works kind of the same way, but instead of doing training all at once, you're training incrementally. So as you're receiving data, you're continually training the model to predict what the next value should be. So this is an example of just when you're trying to predict the next value of the price. But this means that the training happens incrementally, and we need an event-driven system in the middle that kind of handles both the data ingestion and from the real-time data source, and then an online model which is continually retrieving that data and then making predictions in real time. So there's a library called River, which implements a lot of online versions of offline models. So here I'm setting up an online modeling pipeline with a linear regression model that should learn in an online fashion. So that means that we can provide it with single instances from it to learn on instead of providing an entire data set. So this is like one way that you can implement an online learning workflow. So the idea is that we do a prediction and then you learn on a single instance. Once you have the estimated value and the true value, you can compute the loss just like you would in like an offline model, but instead we're learning more incrementally. So this is an example of what that might look like in action. This is kind of a toy example, so it's not really meant to be very accurate, but basically what you can see here is that this is like an example of like a real-time graph. So when we first deploy the model at the left, it's not very good because we have to make a guess about what the model parameters are and what it means to really predict, the stock price of Apple or something. But over time, you might see it start to converge to the true price because because as we continually learn, the loss should hopefully decrease and should start to approximate the true model. So in that way, it's kind of learning more automatically than on like a historical data set. Another example I have is reinforcement learning. So the idea in reinforcement learning is that you have an agent that is interacting with an environment that learns a policy to maximize some reward. Usually this comes up in the context of games because that's a very easy way to understand this problem because games usually have a set action space and you're trying to learn some like obscure set of rules or strategy to maximize a score or like complete a game or something like that. Most famously, this came up in AlphaGo. So AlphaGo is a model that learned how to play the board game Go, basically by playing itself a bunch of times. So you can kind of do a similar thing with other games. So this example is using Tetris. So in the game of Tetris, you're trying to complete rows of blocks by placing the blocks in certain positions, but it ends up being kind of a weird stochastic problem because the blocks are selected randomly, and as you place blocks, it does change the state of the board. So it makes it a very interesting problem for reinforcement learning. So what a reinforcement learning model is doing is that for every state in action, it's trying to learn a policy to maximize the reward. So you get like a probability distribution for each state that you are in the game. So there's a library called Gymnasium, which you can use to model this environment. So it gives you an environment for where you can start experimenting with reinforcement learning models. So here we have to define a set of valid actions that I can pass to the game, say like assuming I'm running the game in like some window or something. And then I have an action space I have to define, and then an observation space, which is what the model will actually observe. So it has to use those things to interact with the simulation and then retrieve data from the environment. And then when we do a training, what we're actually doing is we have to implement a step function, which takes an action. So the policy will give us the action. We have to return the reward for that action. So this is like where the ingenuity comes in. We have to determine what reward function will actually produce a model eventually, which will understand how to play the game Tetris. So here I'm using a pretty naive way of doing it, where I'm just capturing the current score from memory, and then like if you do a move that produces a good score or like a positive score, then we reward that action. Otherwise, like if you reach a game over state by filling up the stack of blocks, then like it's a game over. And so we want to incentivize that. And then that's only part of the puzzle, right? So we also have to define what policy to actually learn how to learn that policy. So stable baselines is a set of open source implementations of reinforcement learning algorithms. So here we are instantiating a PPO trainer. So this is the proximal policy optimization. It's one of the most common ways of implementing a reinforcement learning algorithm. So basically it learns incrementally to not basically over exaggerate from small rewards and attempt to gradually approach an effective model. So here I'm instantiating the policy and I'm also including some logging too. So how does this work in practice? So on the left here is a random baseline. This will be if you're just making random decisions in the game, and it turns out that that's not a good strategy. But after we train it a bunch of times, we speed up the simulation, so we get like 100 or 1.6 million steps. You can start to see that the model actually starts to make some good decisions. That's at least completing some lines, which you'll see in a second. But it's an example of where you can use rule-based rewards to improve the ability for the model to actually interact with this strange environment. So what does this have to do with LLMs? So a good place to start is probably with DeepSeek. So the famous, more famous DeepSeek now. Originally, their R10 model, what they are trying to do is use reinforcement learning to train a language model to learn how to reason about specifically math and coding problems. It's very important that they were trying to do that specifically because it turns out that you can model those based on rules, so you don't need much human intervention in that case to actually compute whether or not the generated tokens were correct, because you can look at the end and see that, okay, it got the right answer eventually. So that's an example of rule-based rewards. So what they did is like they just sampled multiple outputs from each of the prompts, and then they built the system which could learn by itself on a bunch of math and coding problems, and it turned out to be pretty good. But the main problem that they encountered with this model is that it wasn't very usable by humans, as they state in the paper. Their R10 model struggled with challenges like poor readability and language mixing. So because it was trained on Chinese and English, it would kind of mix those when it produces the output. Now that's not very useful from a human perspective, because I want to look at the reasoning and see if it actually understood how to solve the problem, or because that's kind of part of the use of these assistants, which are supposed to reason or resemble reasoning. So basically what they ended up doing was incorporating a lot of human based data. So they used some data just to initially cold start the model from humans, and they also did a supervised fine-tuning stage, and then they used a reinforcement learning stage to align the model to human expectations. So in addition to the rule-based rewards, like we were doing kind of with the Tetris example, they're using human preferences to help improve the helpfulness and harmlessness of the model. So at the end of the day, they needed to have some way of computing how useful the outputs were actually to humans. So I think what we can learn from that is that reinforcement learning with rule-based rewards did help achieve accurate results, but what they really were looking for is alignment. So they wanted the model to align to what the users were expecting the model to produce. So that is one lesson I think we can all take as we're interacting with and training large language models, is that we need to understand how they're going to be used in production and align them to human expectations. One way you can do this is that we can collect data for reinforcement learning with human feedback. So there's a bunch of rule signals that we can collect. So there are readability metrics we can get from libraries like TextStat. So it gives you like the grade level for a specific set of text, which you can use to, maybe you're training a model, but you want the model to be more accessible to users who are not past like the 7th grade reading level. So that is one way you can make models more accessible, is that maybe you want to introduce a reinforcement learning loop where you're training the model to produce text that is more readable. The other approach is feedback based. So this is when you need to solicit human opinion, which I believe is going to get used more and more. So preferential voting is probably the best way we have of doing this, where basically you're presented with two options, and you have to decide as a human, like if you're the annotator, like which is better. That's really the best way we have of determining human preferences, the side-by-side thing. There are also other signals that we can collect from this, like likes and dislikes. So if you're interacting with an application, an LLM application, you might see like the like and dislike thing. You can also collect information about what code is being copied, or where text is being copied to the clipboard, or if the user is regenerating responses. Those are all signals that if you're building your own application, you could collect in order to eventually improve your model. There are also implicit signals as well. So maybe the length of conversations that are happening and the general user engagement with the app are both all signals that you can collect for the purpose of RLHF. Okay, so how does this work in practice? Well, for DeepSeek, a lot of that was offline reinforcement learning because they had data already, and then they just ran through a loop over that data basically to produce the R1 model. But it turns out we can actually do a similar online modeling approach that we did with the online regression, except now we're wanting to improve a language model with human feedback. So basically what this means is that we can deploy a model somewhere that has a PPO trainer attached to it, which is learning the reinforcement learning policy. But it's also getting data back from the user through an eventing system. So this might be like a pub subsystem in like one your favorite cloud vendor or in from Apache Kafka. So basically we're receiving information about interactions. So this is like what interactions is the user doing? Are they liking or disliking certain messages that are being generated? And then we're also retrieving responses from the model to give them back to the app. So it's an example of like training a language model incrementally in an online fashion. So if you use the transformer reinforcement learning library before from Hugging Face, you may already be familiar with supervised fine tuning. So this is like where you're taking a base model and you're training it on domain data to produce a domain specific model or a task specific model. That's kind of like a version of reinforcement learning. There's also you have a PPO method as well, which you can use on human preference data that you're collecting in real time to align a model. You can also do the training offline too. But for this example, we're experimenting with an online approach to doing this. So basically, when we instantiate the real-time trainer, we're setting up the model, and then we're the base model, and then we're creating a parameter fishing fine-tuning adapter on top of that, and then we're training that adapter with a PPO. So basically, what that means is that we have to use the auto model for causal LM with value head instead of the a normal causal LM, because that actually gets us the values that we need to for PPO training. And then what we eventually have to do is that we'll have some functional approach because this is event-driven system. So we have a function we have to process that has to process the rating data that we're receiving from the application. And then we also probably have to cache some data about ongoing conversations so we can map back ratings to what the actual queries and responses were. But we have to come up with a function which converts a user rating or user signals into rewards. So you can use a function like the rating to score I have here, which is just a very simple, like if it's positive, it's 1, negative, it's -1. And we turn that into an actual reward tensor to train with the PPO trainer. So we're just using the step function to do one step of training for each individual sample that we retrieve. And you can also do this in a mini batch fashion too if you don't want to do it on a single instances. So this is kind of what it would look like in practice. So I have the application on the right where the user is publishing messages and getting responses back and then rating the interactions of the model. And then the PPO trainer is subscribing to interactions, and it has to process both the the inference requests and also the training requests, which are coming from the ratings and the conversation from the user. Okay, so major takeaways from this is that real-time machine learning models are designed for data that's expected to change over time. So if you have a system where you're expecting trends to, or you're expecting to observe trends that you can't really predict, that's a good use case for real-time machine learning. And LLMs, I think what we learned is that they require human alignment for success. So really alignment is kind of your new F1 score of accuracy. Like you care usually more about that because I've seen situations where you spend a lot of time training a model and then you don't ever put it in front of humans, and then it turns out that that's not really what they wanted. If the end target is a human user, we need to align them to human preferences. One way we can do that is with RLHF. So it's a reinforcement learning approach, which can be done both offline and online. So basically there's a DPO, direct preference optimization, which is like more of an offline version of what I was talking about, but it's basically instead of reinforcement learning, it's taking human preferences and aligning models, LLMs to those preferences in more of a direct fashion. And then finally, adaptive learning systems, I think they're cool. They do require a substantial engineering effort to build and maintain, because they have to make sure that these systems are still useful and that they're producing safe outputs, especially in the realm of language models, because of how stochastic and and how they can produce confabulations and hallucinations. We need the proper guardrails in place to make sure that they're producing safe outputs. Okay, so if you're interested in more real-time learning examples, I am actually writing a book about this right now with my coworker, which is currently in development, but you can actually read the first 3 chapters. And we've implemented, like the goal for this book is, can we build a step-to-step guide of implementing real-time machine learning with practical Python examples that you can run on your laptop without having to use a cloud resource or something like that. So it's very in line with a lot of the examples you saw in this presentation. So it might be interesting to you if you enjoyed this talk. So I think I have some time for questions now.
Thank you very much. Let me check if we have any questions. Not yet. Maybe just wait a few seconds.
Yep.
Just one question about snow in Minnesota. That is.
I think it all melted. So in Fahrenheit, it's about in the 40s right now. So it's above freezing. So we're not really getting any accumulation of snow anymore, but I think it did snow this week. Snow and rain.
Yeah, okay.
And approaching spring weather.
I didn't see any other questions. So thank you very much. It was a pleasure, and for sure I will be looking forward for your book.
Thank you. Thanks for listening, everybody.